Okay, so here we're going to move on to the second type of question, which is to simplify a set of trig ratios to a single trig ratio. So what we have up here, these ones are pretty simple compared to those that you'll see we'll be facing with example 3 and with further sheets that I'll cover here. These ones are really just to kind of get you in the swing of being able to recognize patterns that kind of hint that you should be using your identities. So when we look at the first question here, 2 sine of 5 times cosine of 5, we're going to look back to our question bank and see if we can find an identity that kind of resembles that. And in fact, we do have one that is just like that. If you look at the sine 2 theta is equal to 2 sine theta cosine theta, that second half, the right side of the equal sign there, matches this perfectly as far as format. So we know we can use that identity to help us here. So I'm just going to copy it down. 2 sine theta, or sorry, sine 2 theta is equal to 2 sine theta cosine theta. And I'm just going to sub in the 5s for our theta values. So we know that here we have 2, or oh my goodness, how should I, yeah, sine of 2 times 5, because we can see that that's our angle measure over here, is equal to 2 sine of 5 cosine of 5. So when we solve this side out to get our single trig ratio, left with sine of 10. So that is equal to our original problem, but it's just written in a much more concise format. Looking down here, we can see that this problem, 2 sine of pi over 2 cosine pi over 2, follows the same format as the one up here, where it's following that sine double angle identity. So we can say 2 sine theta cosine theta is equal to 2 sine pi over 2 cosine pi over 2, which is equal to sine of 2 times theta, as we said up here, and our theta in this question is pi over 2. And these cancel, so we're just left with sine of pi. Alright, down here, same exact thing. It's that sine double angle identity. So we can say that our 2 sine 4, or 4 pi, sorry, cosine 4 pi is equal to our sine of 2 theta. In this case, theta is 4 pi. So is equal to sine of 8 pi as one trig ratio. Okay, so now moving on to part D, we're dealing with a different type of format here. So we have cosine squared theta minus sine squared theta is our format. So looking here, that matches with this identity here, which is a double angle for cosine. So we have cosine of 2 theta is equal to cosine squared theta minus sine squared theta. And you can see that our theta value is going to be 0.4. So we look at cosine 2 times 0.4. Our final value is going to be cosine 0.8. Looking at this problem, part E, our format is 2 cosine squared theta minus 1. we look back here and we see that that's another one of our cosine double angles, 2 cosine squared theta minus 1. So we can copy that over to our double angle cosine equal to 2 cosine squared theta minus 1. We can obviously see that the theta value is going to be 6. So cosine of 2 times 6 is cosine 12. And finally, for part F here, we see that our trend is 1 minus 2 sine squared theta. That's another one of our cosine double angles. These questions, I don't think you'll see them very much. These are really just to kind of get you familiar with the identities that you'll be working with. So that when you come to solving the more difficult problems where you kind of need to know those identities off the top of your head, you kind of have experience working with them. So cosine 2 theta, our theta value, lining these up is going to be pi over 4. So you have cosine 2 times pi over 4, which this cancel, 2 will become a 1, 4 will become a 2, cosine pi over 2. Alright, so now moving on to our last set of example problems for this page. This is really where you're going to see the simplifying come into place. These are the real simplifying kind of problems, that second type of problem that you'll see with trig identities. These are where it comes into place. So taking a look at part A right here for these simplifying problems, the given problem is cosine theta times tangent of theta. When you're looking at these, it says on the right here, strategies for simplifying. Change any values you have in terms of sine and cosine, substitute identities, use manipulations, try something. That last one is really, really pertinent. A lot of it just comes with trial and error. I know that when I was doing a lot of the other problems on these sheets that I'll be going over, the first thing that I tried didn't work, so I just kind of had to like scribble it all out, get a new sheet of paper, and try again. There's really no, I mean, you can see some trends, but really it's just kind of knowing what you have to work with and having the skills to just kind of like stay persistent at it and really just keep like chipping away at it. So looking at this first problem, we have cosine theta again times tangent of theta. So change to sine cosine is going to be really pertinent for this first problem because we have a tangent value. So I'm going to rewrite cosine theta. Tangent, remember, from our identities can be written as sine over cosine. So I'm going to write times sine theta over cosine theta. And because we're multiplying, these cosines will actually cancel out and you'll just be left with sine theta. And there you go, we've simplified it to one trig equation here. So first question done, part A done. So moving on to part B. I know these are really, really small. I can try to zoom in a little bit. I hope that helps. Maybe. Yeah, that looks like it helped. Okay, so our problem is 1 minus cosine squared theta over 1 minus sine squared theta. And whenever you see a 1 minus either a cosine squared or a sine squared theta, it's going to be a real giveaway that you're working with a problem that's involving the Pythagorean identity. So here you have 1 minus cosine squared theta, and I'm just going to bring over our Pythagorean identity so you can kind of see what I mean. So just with some manipulation of the Pythagorean identity, you can see that when you bring either the cosine or the sine value over, to get one of them alone on the left side here, that the right side is going to be 1 minus whatever the other function that you're not getting alone over here would be. So when you're looking at both the numerator and the denominator of this problem, where it's 1 minus cosine squared and 1 minus sine squared, you know that they got the 1 minus cosine squared by subtracting cosine from both sides of your Pythagorean identity. They got the 1 minus sine squared by subtracting the sine squared from either side. So if I was to have subtracted sine squared, I would have been left with cosine squared is equal to 1 minus sine squared. So because we can recognize that, we know that these values, whenever we can recognize this kind of a pattern, the 1 minus whatever squared, you know that the single function value that it could be substituted in for is going to be whatever the other function was. So in this case, we can see that 1 minus cosine squared theta can be substituted in for sine squared theta, and likewise the 1 minus sine squared theta we can substitute in cosine squared theta, because that's what would be left alone on this left side here, depending on what we're subtracting over. So now that we have this kind of ratio, you can see that sine over cosine, that should be ringing some bells as far as like tangent, but like we did in our first problem, because this is not just sine theta over cosine theta, we have to adjust what our, we have to manipulate our tangent expression to match. So this is going to become tangent squared theta. And that's our final answer, because it's one term. So yeah, that's kind of a good example of, you know, just being able to kind of go with the flow with these. Part C, you can see that we have a multiplication problem set up here, a function set up. So first thing I'm going to do to just kind of spread things out is I'm actually going to do double distribution to get single terms that aren't in parentheses here. So we have 1 times 1 is 1, 1 times negative sine x, then you have positive sine x times 1, which is just positive sine x, and then positive sine x times negative sine x, which is going to become negative sine squared x, because you're multiplying two sines together. So now that we have all of our individual terms here, we can cancel these two, because it was a positive and a negative sine x, so those are going to be like, if I subtracted and then added something back, it wouldn't make sense. You can just kind of get rid of those. And you're left with 1 minus sine squared x. And this should, again, like our last problem, be ringing bells of your Pythagorean theorem identity. Because you have 1 minus sine squared, you know that the other side of your equation would be left with a cosine squared. And that's going to be your final answer, because that's one term. I'm sorry if it seems like I'm not really going into much depth about you know, how to explain these. It's really just kind of being able to manipulate equations to look for the patterns that you're seeing. So I recognize that I have 1 minus cosine squared or sine squared a lot, and you know, you can kind of you know, just get used to knowing, and after you sub it in so many times, you'll kind of just have it right there in your brain that whenever you see that it's going to be a 1 minus sine squared x, it's going to be a cosine squared x. So it's really just doing practice problems, developing routine, and getting these kind of problems in your head so that they're right there when you're taking your assessment. So our last equation here, 1 minus cosine squared x over sine x. So again, right here in part D, we have another one of those Pythagorean identity patterns, the 1 minus cosine x, and we know that it's going to be the opposite function left over on the other side of the equal sign. So we know that's going to be sine squared x, And we already have on the bottom here a sine squared x. So that's just going to come out to equal 1. And because that's, oh, sorry, wasn't on screen there, but because that just comes out to equal 1, that's one term, and we're good. That's all we have to solve for. It doesn't really matter that there's no identity in it because it's simplified, and that was the instructions. It doesn't say simplified to a single trig function, it just says simplify, and that's simplified. So looking at the last page here, I just want to kind of go over two quick things, but I'll just send you the answers to this page like I did before, because we've done all of these kind of problems. The only thing I'm not really sure is question 4 and 5 here. We didn't really cover those. I couldn't find anything in my high school notes about how to solve those, and I don't want to give you false information. So considering they're not really about trig identities, I'm just kind of like not going to go over them, and hope that maybe, you have something in your notes that can help you out there. But looking back up here to trig identities, it says up here in problem 1 that we're given sine theta is equal to 1/3, and that the theta value is acute. So acute we know means from 0 to 90 degrees, so we know that we're working in quadrant 1 again, and that all of our trig values should be positive as long as we're working with that same theta value. So our cosine value here in part A, we know that that should be positive. Looking down here to part 2, we're given that cosine theta is -1/2, and that theta value is obtuse. So obtuse means from 90 to 180. So from 90 to 180 on that side of the unit circle, which I've filled in here. So we're working there. And when we fill in our all students text constantly, we can see that in that corner of our unit circle, just sine should be positive. So I've written that down here, that sine is positive, cosine and tangent are negative, and that'll help us with our part A of this problem because we'll be able to see that the value we find there should be positive. So I will write down all these problems, send a picture to you, and hopefully you can kind of do them on your own, check back, see how you're doing. So yeah, good luck with those.